There are moments in human history when the ground beneath our certainties begins to tremble, not with violence, but with a subtle, creeping unease that whispers, "What if everything we thought we knew was merely a shadow on the wall of a cave far deeper than we imagined?" We build our understanding of reality like architects constructing cathedrals, each stone of knowledge carefully placed upon the last, reaching ever skyward towards some ultimate truth. But what happens when the foundation itself proves unstable? What happens when the very cosmos refuses to obey the equations we've carved into the bedrock of our scientific faith? For generations, we've gazed into the night sky with a particular kind of confidence. We've measured the stars, calculated the distances between galaxies, and traced the light that has traveled billions of years to reach our telescopes. We've told ourselves a story about the universe, a grand narrative of cosmic birth and expansion, of dark energy and gravitational waves, of a reality that, while complex and often counterintuitive, ultimately makes sense within the framework we've constructed. This story has become so familiar, so deeply embedded in our collective understanding, that we've almost forgotten it's a story at all. But the universe, in its infinite indifference to human comprehension, has begun whispering secrets that don't fit the narrative, data points that refuse to align, measurements that contradict each other with a stubbornness that grows more pronounced with each passing year. The expansion of space itself, that fundamental phenomenon upon which so much of modern cosmology rests, has started behaving in ways that defy our most sophisticated models. And the scientists who dedicate their lives to understanding these cosmic mysteries find themselves in an increasingly uncomfortable position, caught between the elegance of their theories and the stubbornness of reality. Imagine standing at the edge of an ocean, watching the waves roll in with perfect regularity. You've studied these waves, measured their height and frequency, developed equations that predict their behavior with remarkable precision. You've built an entire understanding of oceanography based on these observations. Then one day, without warning or explanation, the waves begin moving at different speeds in different directions. Some accelerate impossibly, others slow to a crawl. The rules you've relied upon no longer apply, and the ocean you thought you knew becomes alien and unknowable. This is where cosmology finds itself today, standing at the shore of an expanding universe that refuses to expand according to the rules. The crisis brewing in modern physics isn't the kind that makes headlines or captures the public imagination with the same intensity as, say, the discovery of a new particle or the detection of gravitational waves. It's quieter, more insidious, the kind of problem that gnaws at the foundations of understanding rather than exploding them outright. It's called the Hubble tension, and while the name might sound technical and abstract, its implications reach into the very heart of what we think we know about reality. At its core, the Hubble tension represents a fundamental disagreement about how fast the universe is expanding. This might seem like a simple question with a straightforward answer, but in cosmology, nothing is simple. And straightforward answers have a habit of dissolving upon close examination. Two different methods of measuring the expansion rate, both sophisticated and refined through decades of careful work, give us two different answers. And the gap between these answers has widened to the point where it can no longer be dismissed as a minor discrepancy or experimental error. Something is genuinely wrong, either with our measurements, our theories, or both. To understand why this matters, we need to step back and consider what the expansion of the universe actually means. This isn't like watching a balloon inflate from the outside, where you can see the rubber stretching and the surface area increasing. We exist inside the expansion, embedded within the very fabric of space that's stretching. Every galaxy, every cluster of stars, every point in the cosmic web is moving away from every other point, not because they're traveling through space, but because space itself is growing between them. It's a concept that defies everyday intuition, that requires us to think about reality in ways our evolution never prepared us for. Edwin Hubble, the astronomer whose name now graces both the famous space telescope and this troubling tension, made the observation in the 1920s that distant galaxies appeared to be moving away from us, and the farther away they were, the faster they seemed to be receding. This wasn't because Earth occupied some special position in the universe, some cosmic center from which everything fled. Rather, it was evidence of a universe in expansion, where the distance between any 2 points increases over time. From this observation grew the entire framework of modern cosmology, including the Big Bang theory and our understanding of the universe's age and ultimate fate. The rate of this expansion came to be known as the Hubble constant. Though calling it a constant is somewhat misleading, it's more accurately described as the Hubble parameter, because its value actually changes over cosmic time. But at any given moment in the universe's history, there should be a single, definitive value that describes how fast space is expanding. Measuring this value with precision has become one of the holy grails of cosmology, not just because it's an interesting number, but because it's intimately connected to everything else we think we know about the cosmos. Here's where the tension emerges. When cosmologists measure the expansion rate using observations of the early universe, particularly the cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space, they arrive at a specific value. This method involves looking at the baby picture of the universe, at light that has traveled for nearly 14 billion years to reach us, and using our best theoretical models to extract information about cosmic expansion. It's an extraordinarily sophisticated process, relying on our understanding of fundamental physics and the evolution of the universe over cosmic time. But when other scientists measure the same expansion rate using observations of the nearby contemporary universe, looking at supernovae and variable stars called Cepheids in relatively local galaxies, they get a different answer. Not slightly different, not within the expected margin of error, but significantly, stubbornly, reproducibly different. The early universe method suggests the universe is expanding at about 67 kilometers per second per megaparsec. The late universe method suggests it's expanding at about 73 kilometers per second per megaparsec. To the uninitiated, this might seem like a trivial difference, a small percentage discrepancy that could easily be chalked up to measurement uncertainty or some minor correction factor we haven't accounted for. But in the precision world of modern cosmology, where measurements are refined to incredible levels of accuracy, this gap represents a profound puzzle. It's as if you measured your height in the morning and the evening using 2 different, highly calibrated rulers, and they consistently gave you answers that differed by several inches. Either one of the rulers is wrong, or something very strange is happening to your height over the course of the day. The scientists involved in these measurements aren't amateurs or careless observers. These are teams of world-class researchers using state-of-the-art instruments and techniques, checking and rechecking their work, hunting for possible sources of error with the kind of obsessive attention to detail that defines cutting-edge science. The early universe measurements come primarily from the Planck satellite, a space observatory that mapped the cosmic microwave background with unprecedented precision. The late universe measurements come from years of careful observations using the Hubble Space Telescope and ground-based observatories, looking at cosmic distance markers with extraordinary care. Both sides have legitimate claim to accuracy. Both have refined their methods, accounted for known sources of error, and produced results that are internally consistent and reproducible. And yet, they disagree. This isn't a case of one group making an obvious mistake that the other can point out. It's a genuine deep tension in our understanding, and it's getting worse rather than better as measurements become more precise. What makes this particularly unsettling is that the disagreement isn't just about a number. It's about the fundamental story we tell about the universe and its contents. The expansion rate is woven into nearly every aspect of modern cosmology. It affects our calculations of the universe's age, the distance to faraway galaxies, the amount of dark matter and dark energy in the cosmos, and the ultimate fate of everything that exists. If we don't know the true expansion rate, then we don't really know these other things either. Our cosmic certainties begin to crumble. One possibility, the most conservative and perhaps least interesting, is that there's some systematic error in one or both of the measurement methods. Perhaps the cosmic microwave background measurements are being thrown off by some subtle effect we haven't fully accounted for, some foreground contamination or theoretical assumption that doesn't quite hold up under scrutiny. Or perhaps the local measurements are being affected by peculiar velocities of galaxies, by the gravitational influence of massive structures, by calibration issues with the distance markers we rely upon. Scientists have been hunting for such errors with intensity, and while they've found and corrected various small effects, nothing large enough to explain the discrepancy has emerged. Another possibility, more intriguing and more troubling, is that our theoretical framework is incomplete or incorrect. Perhaps the standard model of cosmology, the lambda cold dark matter model that has served us so well for decades, is missing something crucial. Maybe there's new physics at play, some feature of dark energy or dark matter that we haven't yet discovered, some subtle effect that causes the expansion rate to behave differently than our models predict. This would be exciting in one sense, because new physics means new discoveries and potentially revolutionary insights. But it would also mean that much of what we think we understand about the universe rests on shaky ground. The implications ripple outward from this central tension, like waves from a stone dropped in still water. If the universe is expanding faster than we thought, based on the local measurements, then it's younger than we calculated, which creates problems for our understanding of how stars and galaxies formed. You can't have structures that appear older than the universe itself. Yet some of our oldest star clusters seem to push uncomfortably close to the universe's age, as calculated from the higher expansion rate. Something doesn't add up. Alternatively, if the early universe measurements are correct and the local ones are wrong, then we need to explain why our nearby universe appears to be expanding faster than it should. Is there something special about our cosmic neighborhood? Are we in some kind of local void, an underdense region where expansion behaves differently? Such an explanation would require abandoning one of the core principles of cosmology, the cosmological principle, which states that the universe is homogeneous and isotropic on large scales, that there's nothing special about our location. Breaking this principle would require extraordinarily good reasons and would fundamentally reshape our understanding of cosmic structure. Some researchers have proposed exotic solutions. Maybe the nature of dark energy has changed over cosmic time, evolving from one form in the early universe to another form today. Maybe there are additional types of neutrinos or other particles we haven't detected yet, contributing to the cosmic energy budget in ways that affect expansion. Maybe gravity itself behaves differently on cosmological scales than Einstein's general relativity predicts. Each of these possibilities opens doors to new physics, but each also requires us to complicate our theories in significant ways, adding new components and parameters to explain something that should, in principle, be straightforward. The scientific method, at its best, involves a delicate dance between theory and observation. Theories make predictions. Observations test those predictions. And when discrepancies arise, we either refine our measurements or modify our theories. The Hubble tension represents a moment when this dance has stumbled. The observations refuse to align, and the theories don't seem flexible enough to accommodate both sets of data without breaking something else in the process. We're caught in a state of uncertainty, aware that something is wrong but unable to identify exactly what or how to fix it. This uncertainty is uncomfortable, particularly in an age where science is often presented to the public as a collection of certain facts and settled truths. We want definitive answers. We want to know how old the universe is, how fast it's expanding, what will happen in the distant future. The admission that cosmologists don't actually know these things with certainty, that our best measurements contradict each other, can feel like a failure of science itself. But in reality, it's the opposite. It's science working exactly as it should, confronting anomalies honestly, rather than sweeping them under the rug, acknowledging the limits of current understanding while working tirelessly to expand those limits. The history of physics is filled with moments like this, periods of crisis when accepted theories failed to account for new observations. The orbit of Mercury didn't quite match Newtonian predictions, leading eventually to general relativity. The blackbody radiation spectrum didn't fit classical electromagnetic theory, opening the door to quantum mechanics. Each crisis, once resolved, led to deeper, more comprehensive understanding. The Hubble tension might represent a similar turning point, a crack in our cosmic edifice that, when properly investigated, will lead to profound new insights. But there's also the possibility, less discussed but worth considering, that we're bumping up against fundamental limits of what we can know about the universe from our particular vantage point. We exist at a specific moment in cosmic time, in a specific location in space, with access to a specific range of observations constrained by the speed of light and the finite age of the universe. Perhaps some cosmic truths remain forever beyond our reach, not because we lack intelligence or instruments, but because the universe itself obscures them from any observer bound by the same physical laws that govern all matter and energy. This is a humbling thought, one that goes against the optimistic narrative of inevitable scientific progress. We like to believe that given enough time and resources, humanity can understand anything, can crack any cosmic code, and reveal any hidden truth. But what if the universe is under no obligation to make itself comprehensible to beings like us? What if there are aspects of reality that remain intrinsically, irreducibly mysterious? Not through any fault of ours, but simply because we're embedded within the very system we're trying to understand. The expansion of the universe, when you really stop to contemplate it, represents one of the most bizarre and counterintuitive discoveries in the history of human thought. For millennia, we assumed the cosmos was static, eternal, unchanging in its essential structure. The stars might move in their courses, planets might wander across the sky, but the universe as a whole seemed fixed and permanent. This assumption felt natural, obvious, requiring no justification. It aligned with our intuitions about permanence and stability, with our deep-seated need to believe in something unchanging amid the chaos of earthly existence. Then, in the span of a few decades in the early 20th century, this ancient certainty evaporated. Einstein's equations, when properly understood, suggested a dynamic universe, one that couldn't remain static, without the addition of an artificial cosmological constant that he would later call his greatest blunder. Hubble's observations provided empirical evidence that galaxies were indeed receding, that the universe was expanding from some primordial state. The implications cascaded through physics and philosophy alike. If the universe is expanding, it must have been smaller in the past. Follow that logic backward far enough, and you arrive at a beginning, a moment of cosmic genesis that we've come to call the Big Bang. This discovery fundamentally altered humanity's relationship with the cosmos. We were no longer inhabitants of an eternal, unchanging stage upon which the drama of existence played out. We were part of a story with a beginning and, presumably, an end. The universe had a history, an evolution, a narrative arc that could be traced and understood. This realization brought both wonder and vertigo. Wonder at the scope and grandeur of cosmic evolution, at the intricate chain of events that led from the first moments of creation to the emergence of stars, galaxies, planets, and ultimately consciousness. Vertigo at the precariousness of our existence, at the knowledge that everything we see and know emerged from specific initial conditions and will eventually dissolve into some final state, whether that's endless expansion into cold darkness or some other cosmic fate. The expansion rate sits at the heart of this narrative. It determines how quickly the universe has grown from its dense, hot beginning to its current, vast, cold expanse. It sets the timeline for cosmic history, the tempo at which events have unfolded. Change the expansion rate, and you change the story. Make it faster, and the universe is younger. Stars formed more quickly, galaxies assembled on different timescales. Make it slower, and everything stretches out. The cosmic calendar requires adjustment. The relationships between different eras and processes shift. What the Hubble tension tells us is that we don't actually know which story is correct. We have two versions of cosmic history, both supported by solid observational evidence, both internally consistent, and both incompatible with each other. It's as if archaeologists discovered two different sets of ancient records describing the same civilization, equally authentic and authoritative, but giving contradictory accounts of when key events occurred. How do you reconcile such a discrepancy? Which version do you trust? Or do you conclude that both are partially right and partially wrong, corrupted by some systematic error or bias that affects each differently? The scientists working on this problem have explored countless possible explanations. Maybe the cosmic microwave background, that echo of the Big Bang, isn't as pristine a snapshot of the early universe as we thought. Perhaps our galaxy, and others in the local universe, are surrounded by clouds of dust or gas that absorb and re-emit light in ways that affect our measurements. Maybe the assumptions built into our cosmological models, like the precise mixture of different types of matter and energy, don't quite match reality. Maybe the dark energy that drives accelerating expansion isn't constant across cosmic time, but varies in ways we haven't anticipated. Each potential explanation gets subjected to rigorous testing. Researchers develop new models make predictions about what else should be observable, if that particular explanation is correct, then go hunting for those signatures in the data. Some explanations get ruled out quickly when their predictions don't match observations. Others survive longer, remaining viable until someone finds a subtle flaw or a piece of contradictory evidence. It's slow, painstaking work, the kind of science that doesn't generate flashy headlines but represents the true character of how understanding advances at the frontiers of knowledge. One particularly intriguing possibility involves the nature of dark energy itself. This mysterious component makes up roughly 70% of the universe's total energy density, yet we know almost nothing about what it actually is. We've given it a name and can describe its effects, how it causes the expansion of space to accelerate rather than slow down, as gravity would suggest. But its fundamental nature remains one of the deepest mysteries in physics. The simplest explanation treats dark energy as a cosmological constant, a fixed property of space itself that doesn't change over time or vary from place to place. But what if dark energy is more complex, more dynamic? Imagine if dark energy is actually a field, something like an electromagnetic field but operating on cosmic scales, and this field has evolved over the history of the universe. In the early cosmos, shortly after the Big Bang, it might have had different properties than it does today. This evolution could affect how we interpret measurements of the cosmic microwave background, potentially explaining why early universe and late universe expansion rates don't match. Some models of dynamic dark energy predict exactly this kind of tension, making them attractive candidates for solving the puzzle. But accepting dynamic dark energy comes with costs. It complicates our theories significantly, adding new parameters and requiring new physics beyond the standard model of particle physics and cosmology. Scientists are generally conservative about adding such complications, preferring simpler explanations when possible. There's a principle called Occam's razor that suggests we should favor the simplest explanation that fits the data. Dynamic dark energy isn't simple. It requires us to abandon the elegant minimalism of the cosmological constant in favor of something more elaborate and harder to test. Before making such a leap, researchers want to be absolutely certain that simpler explanations won't work. Another avenue of investigation involves the distance ladder, the series of techniques astronomers use to measure cosmic distances. Because we can't simply reach out with a tape measure to determine how far away a galaxy is, we've developed indirect methods that build upon each other like rungs on a ladder. We measure nearby distances using parallax, the apparent shift in position of stars as Earth orbits the Sunday. Then, we use those calibrated nearby stars to determine the distances to certain types of variable stars called Cepheids, which have a reliable relationship between their brightness and pulsation period. Then we use Cepheids to calibrate the brightness of Type Ia supernovae, stellar explosions that serve as standard candles visible across vast cosmic distances. Each rung of this ladder carries uncertainty, and errors can accumulate as you climb higher. If something is systematically wrong with how we measure Cepheid distances, for instance, it would propagate through to our supernova distances, and thus to our measurement of the expansion rate. Researchers have scrutinized every step of this process with extraordinary care, looking for possible sources of systematic error. They've recalibrated using different stellar populations, checked their measurements against alternative distance indicators, employed new statistical techniques to minimize bias. While they found and corrected various small effects, nothing large enough to resolve the Hubble tension has emerged from this scrutiny. The persistence of the tension, despite all this careful work, is what makes it so compelling and so troubling. If it were just a measurement error, the kind of mistake that creeps into experimental science despite our best efforts, you'd expect it to go away as techniques improve and datasets grow larger. Instead, the opposite has happened. As both sides have refined their measurements and reduced their uncertainties, the gap between them has remained stubbornly significant. The statistical confidence that there's a real disagreement, not just random scatter, has grown stronger. What once might have been dismissed as an interesting discrepancy has matured into a genuine crisis. This crisis has implications that extend beyond cosmology into the foundations of physics itself. Our understanding of the universe rests on a few key pillars: general relativity, quantum mechanics, the standard model of particle physics, and thermodynamics. These frameworks have proven remarkably successful at explaining a vast range of phenomena, from the behavior of subatomic particles to the evolution of galaxy clusters. But we've long known they're incomplete. General relativity and quantum mechanics don't play nicely together, giving nonsensical results when you try to apply both simultaneously to extreme situations like black hole interiors or the moment of the Big Bang. The Standard Model works beautifully for describing known particles and forces, but has nothing to say about dark matter or dark energy, which together comprise 95% of the universe's content. The Hubble tension might be pointing us toward the cracks in these theoretical foundations. Perhaps it's revealing that general relativity, while spectacularly accurate on solar system and galactic scales, breaks down or requires modification when applied to the universe as a whole. Perhaps there are additional forces or fields that become important on cosmological scales, but are negligible in laboratory experiments and solar system observations. Perhaps our quantum understanding of vacuum energy and its relationship to dark energy is fundamentally flawed. Some physicists have proposed modifications to gravity that would change how structure forms in the universe and potentially affect expansion measurements. These modified gravity theories typically add new terms to Einstein's equations or introduce new fields that mediate gravitational interactions in ways that become significant over cosmic distances. While these theories can sometimes explain aspects of cosmic acceleration without invoking dark energy, most struggle to match the full range of observational constraints we have from cosmology and tests of gravity in the solar system. It's remarkably difficult to modify gravity in a way that fixes one problem without creating others elsewhere. There's also the possibility that we need to reconsider our understanding of the early universe itself. The cosmic microwave background gives us a snapshot of the universe when it was only about 380,000 years old, the moment when it had cooled enough for atoms to form and light to travel freely through space for the first time. But those first 380,000 years, and particularly the first tiny fraction of a second after the Big Bang, remain largely mysterious. We have theoretical models of this epoch, particularly inflation, a period of exponentially rapid expansion that would have smoothed out irregularities and set initial conditions for everything that followed. But inflation itself is not directly observed. We infer it from its predicted consequences. What if something about our model of the early universe is wrong? What if inflation didn't happen quite the way we think? Or was followed by some additional period of cosmic evolution that left imprints on the cosmic microwave background we're misinterpreting? What if there were multiple fields driving cosmic evolution in those early moments, creating a more complex initial state than our standard models assume? Any of these possibilities could affect how we extract the expansion rate from early universe observations, potentially explaining the tension with late universe measurements. The challenge with all these exotic explanations is that they're difficult to test independently. We can't run controlled experiments on the universe as a whole, can't rewind cosmic history and try different initial conditions, can't peek behind the curtain of the cosmic microwave background to see what really happened in those first moments. We're limited to observations from our particular location in space and time, trying to reconstruct cosmic history from the clues available to us. It's like being a detective who arrives at a crime scene billions of years after the fact, with most of the evidence degraded or destroyed, trying to piece together what happened from fragmentary remains. This limitation is fundamental to cosmology and makes it a peculiar kind of science. In most scientific fields, you can design experiments to test specific hypotheses, isolate variables, repeat measurements under controlled conditions. In cosmology, the experimental apparatus is the universe itself, and it's not exactly cooperative about repeating trials or isolating variables for our convenience. We get one cosmos to observe, one history to reconstruct, one set of cosmic conditions to work with. This doesn't make cosmology less rigorous or scientific, but it does impose constraints on how we can answer questions and test theories. Given these constraints, cosmologists have become incredibly creative about extracting information from the limited data available. They've developed sophisticated statistical techniques for analyzing cosmic structure, for separating signal from noise in faint astronomical images, for testing models against observations even when direct experiments aren't possible. They've learned to combine multiple independent datasets: the cosmic microwave background, galaxy surveys, gravitational lensing, supernova observations, to constrain models in ways that no single dataset could achieve alone. This multi-messenger approach has been remarkably successful, giving us a detailed picture of cosmic evolution that matches a wide range of observations. But the Hubble tension sits stubbornly outside this success story, resisting integration into the neat package of standard cosmology. It's the piece that doesn't fit, the observation that won't be reconciled, the crack in the facade of our cosmic understanding. And perhaps that's exactly what makes it so valuable. In science, anomalies are often more informative than confirmations. When observations match predictions, they validate existing theories, but rarely lead to new insights. When observations contradict predictions, they force us to question assumptions, to dig deeper, to consider possibilities we might have overlooked. The Hubble tension is cosmology's most productive anomaly, the uncomfortable truth that keeps researchers honest and drives them to think more creatively about the universe. As this crisis has deepened, it's also revealed something about the sociology of science and how scientific communities respond to challenges to accepted paradigms. There are researchers who remain convinced that the tension will eventually resolve through better measurements or the discovery of some subtle systematic error. They continue refining techniques, hunting for overlooked effects, approaching the problem with the assumption that our fundamental theories are correct and just need better data. Others have become convinced that new physics is necessary, that no amount of measurement refinement will make the tension disappear, because something is genuinely wrong with our theoretical framework. They're exploring modifications to dark energy, gravity, or other fundamental components of cosmological models. These aren't just different approaches to the same problem. They reflect different philosophies about how science should proceed when confronted with anomalies. Conservative approaches favor incremental changes and systematic error hunting, while revolutionary approaches favor bold new theories and paradigm shifts. Both have their place in science. History shows that most anomalies do resolve through better understanding of systematic errors or more careful analysis, validating the conservative approach. But history also shows that some anomalies genuinely require revolutionary new theories, that paradigm shifts do happen, and that being too conservative can delay important discoveries. The Hubble tension has become a kind of litmus test for these different scientific philosophies. Your position on what's causing it and how to resolve it reveals something about your broader views on the nature of scientific progress and the reliability of current theories. This isn't to say the debate is purely philosophical or sociological. There are genuine empirical questions at stake and real data to analyze. But the interpretation of that data and the strategies for moving forward are inevitably colored by deeper assumptions about how science works and what kinds of explanations we should favor. What makes this moment particularly fascinating is that we're living through it in real time, watching the crisis develop and the community respond, rather than reading about it in retrospect as a settled chapter in the history of science. We don't know yet how this story ends. We don't know if the Hubble tension will be remembered as a brief period of confusion before some clever resolution was found, or as the opening salvo of a revolution that transformed our understanding of cosmology, or even as an enduring mystery that highlighted fundamental limits to human knowledge of the cosmos. In the meantime, the universe continues its expansion, indifferent to human puzzlement about the rate. Galaxies continue receding from each other. Space continues stretching, and the cosmic story unfolds according to whatever rules actually govern it, whether we understand those rules correctly or not. Our confusion, our crisis of understanding, is entirely a human problem. The universe knows what it's doing, even if we don't. And perhaps there's something almost comforting about that, about the knowledge that reality continues operating according to its own logic, regardless of whether we've figured it out yet. The ultimate resolution of the Hubble tension, whenever and however it comes, will likely teach us as much about the process of science as about the cosmos itself. It will show us how scientific communities navigate fundamental uncertainties, how they balance conservatism and creativity, how they deal with the discomfort of not knowing something that seems like it should be knowable. And it might remind us that the universe is under no obligation to make sense to us, that our theories and models are always provisional approximations of a reality far richer and stranger than any framework we construct to contain it.